Here we go. We are going to investigate transformations of functions that are a little bit more difficult. I did a poor job today of anticipating where my learners would be. I thought you guys would remember this much, but first hour and third hour remembered more like, say, this much, okay? So, hey, it's okay. We get it. So, my friend Jada here, she has out her notes, and she's not going to turn to this section of her notes. But if she has her notes, she's going to turn to this section where you have the family of parent functions sitting right there. And that will help jog your brain. I'm sorry, Jada feels insulted. She says she already memorized all the parent functions. She knows all the shapes already. I'm sorry I insulted you. But if you don't remember them, keep it out so you can look at it. So we have y is equal to 1 over x plus 2. What you want to do is graph the new function and state its domain. Everybody should see that this is going to look like y equals 1 over x. And when you sketch that graph, you can see that the reciprocal function that we have looks like this. These are functions that you need to commit to memory. Now we have to decide the transformation. It's 1 over x plus 2. So if you consider that, that's the same thing as, that's slightly different than y is equal to 1 over x plus 2. Notice the difference. Here the plus 2 is on the outside. Here the plus 2 is on the inside. If the plus 2 is on the inside, will that affect it horizontally or vertically? Horizontally. So is it going to move to the right 2 or left 2? Left 2. So therefore, your function, it's making a mess today. Your new function is going to be shifted left 2. And your domain is going to be x not equal to negative 2. I'm trying to teach you two things today, folks. I'm trying to teach you how to transform functions. I'm also trying to teach you how to check domain. If you know how to graph 1 over x plus 2, you should be able to look at the graph and say, oh yeah, x can't be negative 2, but it could be any other value. Hopefully you can also look at this and say, oh yeah, I can't plug in negative 2. I'm trying to give you multiple ways of verifying your answer. The next one, y is equal to x minus 3 to the 1/3 power. You may not recognize this. This is y is equal to the cubed root of x minus 3. Do you recall what a cubed root function looks like? Yeah, it's like something like that, right? So how is this going to be transformed? Close. To the right 3. The 3 is on the inside, so it's going to move right 3 units. Anybody want to know the domain? Anybody know it? All real numbers. Very good. Just look at it. I think it's easier to look at the function and state the domain. Oh, the next one, how is it different than the first? Bottom is squared. What's going to happen if you square the bottom? It can't be negative. If you square the bottom, the parent function, they both want to be above the x-axis. That's what the parent function will look like. So what are the transformations happening here? What is the x minus 3 in the denominator going to do? Shift it to the right 3. Now, never mind the 2 on top. The 2 on top actually creates what we call a vertical stretch. We're going to talk about that later. I want you to actually just, I put the 2 there because I want you to learn to ignore it when you do transformations for the most part. Just ignore the 2. But don't ignore the negative. The negative's on the outside. If you get a negative on the outside, is that going to create a vertical flip or a horizontal flip? Negative on the outside creates a vertical flip. If anything is on the outside, it affects it vertically. Inside is horizontal. Domain x not equal to 3. The next one, y is equal to the square root of 4 minus x plus 1. You remember what the square root function looks like, right? Like that? Great. So what's the plus 1 going to do? Up 1. Yep, the plus 1 moves it up 1. 4 minus x, what would you plug in to make 0? 4. So it's going to move it 4 to the right. It's going to move it up 1. Notice how the x is negative? That's going to flip it horizontally. Very good. Very good. Right 4, up 1, horizontal flip. This one, y is equal to negative x minus 2 to the 5th plus 4. You can rewrite it to look like that. And if you rewrite it like that, you might understand the graph better. X minus 2 to the 5th plus 4. You remember what a 5th degree function looks like? Similar to a third. Very good. Yeah, it's skinnier. Very good. So, what are the transformations then? Up 4? Right 2? Is the negative on the outside or inside? Outside, so that will create a vertical flip. Right 2, up 4, vertical flip. Domain. All reals. Domain for this one was negative infinity to 4. We've already done this one. We know what the parent function looks like. What's the plus 3 going to do? Up 3. Uh-oh. How's this next one different? Fifth power, not fifth root, fifth power. So is it going to look more like the first one or more like the third one? Which one do you think? The first one, why? Because it's an odd degree. Very good. So see how it's an odd degree? So if it's odd degree, they're going to be in opposite quadrants. If they are even degree, they're going to be in adjacent quadrants. Okay? So very good. We know that they're going to be in opposite quadrants. The x minus 3 is going to move it 3 to the right, but notice it also has a negative. So that will flip it. So instead of being in the bottom and then the top, it will be in the top and then the bottom. X cannot be 3. Oh, Mr. Gantz, why do you give us such difficult problems? I don't know. I want to help you think through them. Fourth root. Do you think that's going to look more like a square root or a cubed root? Square root. It wants to look like this. And now you're like, okay, I got that, Mr. Gantz, but there's 2x plus 6 on the inside. Well, hey, it's all on the inside, isn't it? It's all on the inside. What would you plug in to make 0? Negative 3. So it moves it 3 to the left. So when you're wondering about a horizontal shift, just think, what would you plug in to make 0? Domain, negative 3 to infinity. We'll do a few more together. That one's a cubed root, right? We know what the cubed root looks like. What's the transformation? Vertical flip and left 2. That's what I heard. Now, every once in a while, students start to get a little sarcastic with me and kind of judgmental. They're like, well, Mr. Gantz, your graphs are crappy. They're messy. They don't look very good. We're not really doing it justice. Okay? Well, okay, that's your opinion, and you're entitled to your opinion. That's fine. I would disagree. I would say that if I type in negative cubed root of x plus 2 and I go zoom standard, I would say that the resulting function actually looks, well, pretty much what I have up there on the calculator. Does it not? Do you see how quickly we're able to generate these graphs that otherwise look complicated? Just know the parent function and then know the transformation. We try the next one. X to the fifth. X to the fifth looks like x to the third. Yeah, it looks just like a cube. Just down 4 units. And once you do that, it's easy to state the domain. What's the domain? Look at it. It's all real numbers. But you see, if you don't look at the graph, then people do crazy stuff with this. They like set it equal to 0, and they go x at fifth minus 4, and they add the 4. X at fifth, they say x can't be the fifth root of 4, stuff like that. No! Like, I get what you're doing, but no! Don't! Just sketch it. That's actually where it crosses the x-axis, but that's it. Okay, negative x plus 1 to the fourth. To the fourth looks like to the second. Yeah, it's just more narrow. So the parent function looks like, you know, that. So what's this transformation going to be then? Left 1? Upside down. Sweet. All real numbers. Let's do 3 more together. Man, you guys are smart. Good job. I've seen this one before, haven't I? Horizontal shift. Vertical shift is up 2. Horizontal shift is right 3. So I'm going to go right 3. And I'm going to go up 2. Are these going to be in opposite quadrants or adjacent quadrants? Opposite, yeah, because it's an odd power, so opposite. Okay, I want to try this one with you. And I want to try this one with you. We'll be done. Then you can work. I was visiting with some of your teachers who were talking about how our students learn. And they all agreed that you guys are extremely intelligent. We were talking about how we help you learn better. And we agree that we need to not force you to memorize so many things. We need to start helping you think of why things are the way they are. Okay? Understand why they act the way they act. So look at this one. You see this negative x squared cubed root plus 4. And right away you're like, I have no idea what it looks like. Well, you know a cubed root function looks like that, right? You all know that. So what's going to happen if you square something? It's going to make it positive, right? Do you see this? You take something, you square it, makes it positive. So you have a cube root function, but it's positive. That's what the parent function looks like. A cube root function is positive. So what's the transformation going to be? Up 4 and flipped upside down. So it's the bird function, flipped upside down. But notice how you can look at it and understand why it makes the shape that it does. And finally, the last one. We talk about a fifth degree. And this is my trick for you for, again, graphing these type of things. Vertical shift is down 4. What do you plug in to make 0? 2. That's always my trick to you for looking for your horizontal shift. What do you plug in to make 0? So it's over 2. It's down 4. But now, when you multiply this out 5 times, okay, 2 minus x to the 5th power, we multiply it out 5 times. Is it going to be a positive x to the 5th or a negative x to the 5th? It's going to be a negative x to the 5th, isn't it? Yeah, so it's going to start up and finish down. And that's that. That's about a third of your work taken care of. I'm going to scan your sheets and send them to Espy so she can upload them. Good? Did we get enough sleep over break? Too much work, huh? Oh, you poor kids. Yeah, we all need sleep.